Alright, what's up everybody? I'm back with another video, and in today's video we're going to do a part 2 example of nodal analysis, and our goal for this video is to find out what V naught is equal to. So basically what this voltage is equal to, right? So the difference between this example and the last example is on the right side there's no voltage source over here anymore, as it's replaced with the resistor. So we're going to see what we can do now to try and find out what V naught is, right? So let's get right into the video. So if you remember before, we know that we have a V1 over here, right? So our first node is over here, second node over here, V3 over here. Now because there is no voltage source on this side, as this resistor circuit is always connected to the reference node, there's actually no node on this corner anymore, as now we just have our regular reference node at the bottom, right? So now we only have 3 nodes or 4 nodes including the reference node on the bottom, right? So you have V1, V2, and V3, okay? So knowing that, let's draw where our currents go. So we have an I1 that comes this way. We have an I2 that comes down. We have an I0 that comes down. And we still have an I3 that goes around over here, right? So we still have our 4 currents. That doesn't change, right? So you have I1, we have an I2, I0, and I3, right? Now, an easy thing that we can also see once again is that in between V2 and V3, there's a 12 volt voltage source, right? And if you guys don't know what I'm talking about with supernodes, please go back and watch part 1 to get a better understanding. But we know that when there's a voltage source in between 2 nodes that are not connected to a reference node, right? So V2 and V3, when we're looking at them in comparison to one another, there's no reference node attached to it, right? So we can't say that V2 is equal to negative 12 volts or V3 is equal to positive 12 volts because their 2 nodes are connected to one another with no reference attached to it, right? So we can make an easy assumption of an equation, right? So we always start from the positive and go to the negative, right? So positive minus the negative. So the positive side is the V3 end, right? So V3 is on the positive end, so we can say that V3 minus V2 is on the negative end of the voltage source, so V3 minus V2 is what's equal to what the change in voltage is described as the voltage source, which is equal to 12 volts, right? So that is what our first equation is going to be. So now that we have our first equation, we need to make a second equation to basically solve what V3 is equal to, right? Because if we look at it this way, guys, right? If we look at it this way, V3, if we look at it where VO is connected directly to a reference node, right? So this cylinder right here, V3 is connected to a reference node. So essentially V3 is equal to VO, right? Because the positive end of this is what V3 is equal to. So this positive end is what V3 is equal to essentially, right? So all we have to do to find VO is essentially just find V3. So if we find another equation with V3 in it and use substitution, essentially we can find out what V3 is equal to, right? So that's essentially what our goal is going to be for this video. Now, from the start, we see that the positive end of the 6 volt source is connected to V1, and the negative end of the 6 volt source is connected to the reference node over here, right? So essentially, we can already determine that V1 is equal to 6 volts, right? So the positive end is connected to V1. V2 is unknown to us, and V3 is also unknown to us, right? So we have to find a way to solve for V3. Now, if you guys remember about supernodes, we can know that we can connect these 2 nodes together if there's a voltage source in between them, and then connect these 2 current sources going down. So if you have I2 and I0 coming down, we can connect these essentially. So we have a supernode in the middle, we have I3 coming this way, we have I0 coming down, and we have I2 coming down from the same node, and we have I1 coming in, right? So we know that current has to equal, current equals the summation of current is equal to 0. So the sum of the current going in has to equal to the sum of the current going out. So essentially it's I1 is equal to I2 plus I0 plus I3, right? So the sum of the current going in, so I1 comes in and I2, I0, and I3 are exiting the supernode, right? And we can assume already that it's a clockwise notation, because if we use our passive sign convention, guys, we can see that the positive end, the I0, is coming down this way, right? So because the positive end is here using passive sign connections, we know that the current always enters the positive side, right? So we can assume that the current is flowing in a clockwise direction, right? So that's why I1 is coming in, and I2, I0, and I3 are what are exiting the supernode, right? So after making that assumption, let's see if we can use our KCL and using nodal analysis to figure out another equation for the supernode, right? So if we have to make an equation for the supernode, let's take a look, right? So we have V2 over here and V3 over here. So let's do what I1 is, right? So what's the equation for I1? Well, I1 is essentially V1 minus V2 all over this resistor source, which is 3 kilo ohms, right? So 3K. That's what I1 is. What about I2? Well, I2, as you can see here, is just going to be coming down this way, and we have V2 minus the reference node. So the reference node, if you guys don't remember, is always going to be 0 volts, right? So 0 volts over here and 0 volts over here, because it's a reference node, so they have no real voltage source. So it's going to be V2 minus 0 volts divided by 4K, because as you remember, V over R is what is equal to I. Well, technically the change in V, the change in voltage. So V2 minus 0 over R is equal to the current source, right? So essentially, because we can take away the 0 volts, as it's not really useful to this problem or question, so we can do V2 over 4K is what is equal to I2, right? So we can go ahead and write down V2 over 4K, which is what is equal to I2 over here, right? So what about I naught? Well, I naught is equal to V3 over 6K, right? As it's the same rules that are applied to the V2 reference node. As if we can look over here, it's still in this V3 minus 0 over 6K, right? So it's V3 minus 0 over 6K to essentially get what I naught is coming down here, right? So that's what V3 is. So if you just erase this again to make it more clear, next we can see we have to find out what I3 is. So if we look at I3, we see that I3 is coming around in this loop. And we said that this node is essentially connected to this reference node, right? So these two nodes are the same. So essentially we have to add these two resistors, and it's V3 minus 0 again, but this time we're adding the 4K plus the 2K. So there's a V3 coming this way down here, which is I naught, and there's a V3 going to the right, which is I3, which is 4K plus 2K, right? So essentially we're going to get plus V3 over 2K plus 4K for what I3 is, right? So essentially we have our I1, our I2, our I naught, and our I3. So that is our nodal analysis equation. So knowing that, we're gonna simplify this further and try to figure out what V1 and probably what V2 and V3 are equal to, right? So if we simplify this further, we get V2 over 4K plus, and then we have 2V3 over 6K, right? So we get 2V3 over 6K, because this essentially is equal to 6K, right? So then if it's V3 over 6K plus V3 over 6K, that's essentially 2V3 over 6K. And this essentially becomes V2 over 4 plus 2 over 6 just becomes 1 over 3. So it's just V3 over 3K. Then we bring this down and we get V1 minus V2 over 3K. Now what we're going to do is that now that we have this equation, we're just going to cross multiply like we usually do, right? So we're going to take this 3K that's over here and we're going to multiply it here. So we're going to multiply 3K over here, which cancels out, and we're going to multiply this whole thing by 3K, right? And that's what we're going to do. So essentially what we get is V1 minus V2 is equal to, what's 3K times V2? So we get 3V2 over 4K, and then this 3K and then this 3K canceled out, so it's just plus V3, right? So now we have V1 minus V2 is equal to 3V2 over 4K plus V3. Now, if you guys remember from the beginning, we said that V1 is equal to 6 volts, because this positive end of the 6 volts is connected to the node 1 over here for V1, and the negative end is connected directly to a reference node. So we can just assume that V1 is equal to plus 6 volts, right? So because we know that V1 is equal to plus 6 volts, we can do 6 volts minus V2 is equal to 3V2 over 4K plus V3. Now we have to get rid of this 4K, so how about we do that? So to get rid of the 4K, we have to multiply both sides by 4. So if we multiply both sides by 4K, right? So we multiply this side by 4K, and we multiply this side by 4K. Let's see what we get. Well, the 4Ks over here cancel out, right? So this 4K and this 4K cancel out. So you're left with 3V2. But then this 4K multiplied by the V3 results in plus 4 V3, and on the left side, I mean, we get 4K times 6, which is going to be 24 volts, minus 4 times V2 is minus 4 V2, right? So essentially what we get, if we simplify this further, is 24 volts is equal to 7 V2, right? Because we bring this 4 over, so it's 3 plus 4 as the sign changes, so it's 7 V2 plus 4 V3. So now that we have this equation, we can essentially say that this is our equation 2, right? So with this equation, we can now put 2 into equation 1. And if you guys remember what equation 1 was, we have that equation 1 is V3 minus V2 is equal to 12 volts, right? So essentially we can say that 12 volts is equal to V3 minus V2, right? So then we can substitute this and we can say that 12 volts plus V2 is equal to V3, or instead we can see 12 volts minus V3 is equal to negative V2, right? So we can say that 12 volts minus V3 is equal to negative V2. So now we have V2 in terms of V3. So if you just make this a positive, we can just multiply it by negative 1, and essentially we get negative 12 plus V3 is equal to V2, right? So now that we have V2 in terms of V3, we can just take this V2 and plug it into the first equation, and then the second equation that we have, which is this one, and we can then solve for what V3 is equal to. So then our equation becomes 24 volts is equal to 7, and then V2 becomes negative 12 plus V3 plus 4 V3, and then we can isolate for what V3 is. So essentially we get 24 volts is equal to what's 7 times negative 12, negative 84 volts plus 7 V3 plus 4 V3, and essentially what we get is 108 volts when we bring this 84 over, so it's 24 plus 84, right? So 108 volts is equal to 7 V3 plus 4 V3 is equal to 11 V3, right? So then if we do 108 volts divided by 11, that is what we get when we isolate for V3, and essentially V3 then becomes 9.81 volts, right? And we can also know that V3 is equal to VO, which is essentially 9.81 volts. And we know that VO is equal to V3 once again because V3 is connected to the reference node, so the plus side of VO is equal to the plus of V3, right? So V3 is essentially equal to VO, so that is our final answer, that VO is equal to 9.81 volts. And this is how we did it using nodal analysis and supernode theorem, right? So if you guys have any questions or concerns about this answer or solution or the problem itself, please make sure to comment down below or email me at sharonacademy@gmail.com. I'll make sure to get back to you and reply as soon as possible. If you guys want to make more videos like this or any specific questions or topics that you guys have, please comment down below once again, and I'll make sure to make a specific video on it as soon as possible. Alright, make sure to like, comment, share, and subscribe if you guys enjoyed and understood it. So if you guys want to see more of this, please subscribe. Thanks again for watching, guys.